Okay, here's a quick video just to test the autofocus. We did 2 videos before, they were a bit blurry. Multiple choice, YouTube 1, part 1 was multiple choice questions, 16 minutes, and then I did manage to do 11, 13, 12 minutes on the other ones. And this is now the autofocus for question 14. So hopefully we can read it. Albert Einstein was awarded the Nobel Prize for Physics. It looks clearer, but it's still not that clear. For his discovery of the law of the photoelectric effect. To explain this, Einstein proposed that electromagnetic radiation should be modeled as a particle rather than as wave. Explain why, when considering this photoelectric effect, treating electromagnetic radiation as a particle is a more successful model than treating electromagnetic radiation as a wave. Well, the way you answer this, 6 points, there's 3 bits to it. So I've divide them into 3 bits. So what we observe in each case and why the comparison between the wave and the particle model is in favor of the particle model. So first of all, we observe that above a certain minimum or threshold frequency, electrons are emitted. If radiation is considered to be a wave, any frequency should be able to provide sufficient energy to release electrons. So the wave model isn't as good as the particle model because it's not what we observe. The reason any frequency should be able to cause electrons to be emitted with a wave model is because waves all carry energy. So if you wait long enough, they will eventually build up enough energy to energize the electron to the threshold energy required for escaping the metal surface. Remember, this happens usually with the metal. And then number 2, we also observe that electrons are released instantaneously, which is what I was saying, suggesting that they get the energy required in one hit, which is kind of the quantum model of physics, which is what the photon is. The photon gives all of its energy in one go. So the photon model is the particle model. So that seems to support also the particle model of light, whereas if radiation is considered, I've written, to be a wave, the energy would take some time to build up to the required amount, and yet it doesn't do that. It comes in one hit. And then finally, in the third point, it is observed that the kinetic energy of the released electrons is proportional to the frequency of the radiation, as long as it's above the minimum that we mentioned in part 1. But if the wave model was correct, the kinetic energy of the released electrons would not depend on frequency, but on the intensity of the radiation, because obviously with a wave model, it's the intensity that correlates with energy. So for these 3 reasons I put, the particle model of radiation is more successful than the wave theory. So that's my answer to question 14. Let's try and do question 15 while we're on it. Yeah, I'll just show you question 13 to see if this is clearer than the last video I had. So if you wanted to go back and look at what I said in the previous video, here is a clearer video. It's still not as clear as I would like it to be. And there's part B. So you'll be able to stop the video and have a look to see my wording of the answer. Okay, so that's 13 and 14 done. Question 15 is about resistors used as potential dividers in a circuit, and they want you to derive an equation for the combined resistance. So in other words, derive the equation for resistors in series. Well, you know that the 2 resistors in series are R1 and R2, so they add up. The voltage across them must add up to the total voltage of the circuit. The current through them both is the same because it's in series. So you know from Kirchhoff's second law that V total must equal V1 plus V2, and you can change V total to I, which is common through the whole series circuit, times the total resistance of the circuit, and likewise the voltage across resistor 1. So if you put a voltmeter across there, it would be the current times the resistance of resistor 1, and likewise for resistor 2. Yeah, now since I is the same throughout, you can cancel the I out in the formula algebraically. You can just cancel it out, so you come up with the formula for resistors in series. And this can apply to any number of resistors, it doesn't have to be 2. And this gets you to 3 marks. You basically get 1 mark for each line. Okay? Looks like the focus is still not the way I want it to be. And then part B, it says the diagram shows a circuit that includes a resistor combination. The battery has negligible internal resistance. Yeah, so you can ignore the internal resistance of the battery here. The current here is 0.5 amps. Now you can do this in multiple ways. So we know the total current, we know the total voltage. So we know the total resistance of all of that. And if you do that, total resistance circuit must be the voltage here divided by the current there, which is 0.5. So total resistance of the circuit is 14 ohms. And you've got 6 ohms outside the parallel part. So you can take away the 6 ohms from the 14 ohms total, and you get, for the parallel part of the circuit, I've called it resistance of the parallel. So that's this bit here. Must be equal to the total resistance minus the 6 ohms, which is outside the parallel combination, which means 8 ohms left for these 3 resistors in combination. So we know that the circuit, the equation for parallel circuit is 1 over the total resistance, which is in this case the 8 ohms, and 1 over R, which is at the top, which we want to find out, of the branch. There you can just see it. Is equal to 1 over 24 for the bottom, so because these two are just added together according to the resistance in series. So you're going to get 1 over 8 equals 1 over R plus 1 over 24. Then it's just a matter of doing the fractional method of solving the problem. I've done it for you, so you should be able to work out that the resistance is 12 ohms. Okay, I'm going to stop the video there. Another short video having gone through questions 14 and 15, and I'll upload it, and hopefully I can still get the focus to work even better next time. Okay, just make sure you like and share the video with your friends, and subscribe so you know when the next video is coming through. Bye for now.